Hello everybody and welcome to week 10. Today we will focus on chapter 6 and finally everything should start becoming easier. The entrance starts defining the inner product on our real vector space V. Now you can see page 335 the definition of the inner product between two vectors u and v. Now almost everything will be vectors, so I won't put any more the arrows and I can write in bold. So this is the inner product. There are some properties that are the one that you already expect, like symmetry, additivity, homogeneity. Just look at the definition. And basically this will be something that we can write like that, is the dot product that you already saw. And we saw that we can do something like this. We can just multiply component by component. So the first one, this is the common product of two real numbers. So this is a real number and this is a real number, plus u2, v2, etc. for the n components that each one of these two vectors has. Now the 2 points that are important in the first paragraph are basically the definition of norm or length and the distance. So basically what we are going to write is that the norm of a vector v, that is its length, is equal to what? Well, the square root of this v. Now what's this? Well, basically you know that when you have the inner product between two vectors, what we are going to do is the product of one vector by the projection of the other vector on the first vector. So if you have the same vector here in the inner product, basically what you are doing is to take the product of the lengths. And if you take the product of the lengths, you will get what you expect. So it's the length squared. The norm, the meaning of the norm, is exactly this. It's just the length of the vector. Now, the distance between two vectors is the second thing. So if you want to know what's the distance between u and v, well, this is defined as the norm of u, just a moment, minus v. Why this? Well, let's explain this a little bit better. Okay, let's say that we have a vector u and a vector v. Okay, if I want to know the length of u minus v, first of all, I need to know what's u minus v, and this is a vector. Now, u minus v is, well, let's just take the usual rules to compute this, and let's draw again u and minus v. You can see this is minus v. See, so u minus v is this vector. This is u minus v. Okay, so this is what we are interested in. So what I'm doing is to compute the length of this vector, u minus v. So the length of u minus v, you know, is this. And this is equal to the square root of u minus v, u minus v. This is by definition. So the distance between u and v is defined as the length of the vector u minus v. Does this make sense? Well, obviously yes. In fact, if you look back at the first graph and I asked you what's the distance between u and v, you would say this. This is the distance between the two vectors. And in fact, this is just the length of u minus v. So we can define this as the distance between u and v. In the second paragraph, the Anton goes through the Cauchy-Schwarz inequality, and you can have a look at that. What is important now is to be able to answer the question, what's the angle between two vectors? Well, you already did this, but just to do again, we saw that theta, the angle between two vectors u and v, so this is theta, is by definition the inverse function of the cosine of a ratio. And this ratio is the inner product, uv, that is a number, remember, over the norm of u and v. Sorry, sometimes I still put the arrow. Let's do everything consistent. Okay. So what happens if I tell you that u is a vector like in the example with components 4, 3, 1, minus 2, and v is a vector with components minus 2, 1, 2, 3. Well, if I ask you what the angle between these two vectors, you know how to compute this. You just have to compute theta with this formula. So this is the inverse of the cosine of what? Well, there is a ratio, and in the numerator there is the inner product. But the inner product is basically very easy to compute. You just have to take the product of these elements, match it one by one in the same order. So is minus 8 plus 3 plus 2 minus 6. And what in the denominator? Well, in the denominator, we just have to take the norm of u times the norm of v. But we know that the norm is just the square root of the inner product of a vector with itself. So we just have to make the square root of 4 squared, so 16, plus 9, plus 1, plus 4, and for v we got 4 plus 1 plus 4 plus 9. Okay, so you just have to solve this, and that's it. You get the angle between two vectors. About paragraph 2, the last thing that is important is to go through example number 6, because example number 6 is a good starting point to review what the orthogonal complement is. In the example, basically we have R6, that is just the R6 space, vector space, and you're given with 4 vectors. W1 is equal to 1, 3, minus 2, 0, 2, and 0. And then you have other 3 vectors. What the question asks you is, well, let's say that W1, W2, W3, and W4 span a subspace of R6 that is W. So you can create a subspace using these 4 vectors. Now, as you can see, each one of these vectors has 6 components because it's a vector that lives in R6, and they create a new subspace just with in which every vector can be defined as a linear combination of W1, W2, W3, and W4. Now the question asks you, find a basis for the orthogonal complement of W. Now, to solve this, you have to remember that if you take a matrix and you make compute the null space of A and the row space of A, where A is this matrix, these two spaces are orthogonal. So basically here the trick is just to create a matrix A in which in each row you just put these vectors. So 1, 3, minus 2, 0, 2, 0, this is W1, and then here you will put W2, W3, and W4. You can follow the Anton. What I want to point you is to just notice, as it is extremely easy at this point to find something that would be very difficult to think of. Now we want to just find a space that is orthogonal to W. And to do this, we create a matrix A using the 4 vectors that span W. And then we just find the null space of the matrix A. Doing this, we find a space that is orthogonal to the row space of the matrix A. And that space, that vectors are the basis for the new space. So let's try to do that. Okay, I have the matrix A that is equal to 1, 3, minus 2, 0, 2, 0, then 2, 6, minus 5, minus 2, 4, minus 3, 0, 0, 5, 10, 0, 15, and 2, 6, 0, 8, 4, 18. What I want to solve is the equation AX equal to 0. Now, solving this means solving exactly the same matrix that you can find in chapter 1, page 16, example number 5, that is titled Gauss-Jordan elimination. So there are some quite boring for me to write here operations to do on this matrix, and what you get finally, just have a look there, is a matrix with these numbers in 1, 3, 0, 4, 2, 0, 0, and then 0, 0, 1, 2, 0, 0, 0, and then 0, 0, 0, and 0, 0, 1, 1/3, and then the last are all zeros. So what here are we getting here? Let's just comment on this. Well, first of all, you can see that we have the leading ones that are here, and that these are all zeros. So the solution of this, if you want to rewrite this in the corresponding system of equations, you can rewrite in this way. You can write that x1 is equal to minus 3 x2 minus 4 x4 minus 2 x5. And then the second equation is x3 equal to minus 2 x4. And the last equation is x6 is equal to 1/3. Okay, this is the set of equations. Now, what can we see from here? Well, basically, remember, we are building a space that is orthogonal to W. And this space has this equation to define it. That means that for each point, if you give x2, x4, and x5, so if you decide three numbers and you assign these three numbers to x2, x4, and x5, you can derive the values from this of x1, x3, and then x6. That is just a constant. You can see x6 is not really very impressive. It's like when you have a 2D space and you fix the value of x. If you fix the value of x, you are just decreasing the dimension of your space by 1, because you are saying, well, every number will be on this line. Okay, was just a digression. Every time you fix a value of one of your components, you are decreasing basically the dimensionality of your space. Okay, so what we are saying is that we just say three real numbers, and then we can derive the other three. That means that this space just needs a three-dimensional basis, right? And what is this basis? Well, that basis is given by this set of equations. And in fact, if you look, you can write something like this. You can say, well, the first basis, V1, will be what? Well, what does it mean that we are going to write a basis for this new space? Well, that means that every point, every vector, will be possible to be written like a combination, a linear combination of three spaces. So every x will be like a linear combination of v1 plus v2 plus v3. That is a linear combination of v1, v2, and v3. And this is what's happening here, basically. So if you want to rewrite v1, v2, and v3, we have to ask themselves which components we have to write here in v1, v2, and v3. Now, here is the magic, and let's change color. What's this C1, C2, and C3? Well, here it is, x2, x4, x5. In fact, and now I can show you that this works, in fact, you have just to decide x2, x4, and x5, and then all the rest is determined. That means that you just have to decide C1, C2, and C3, and then the vector x is determined, given that you have a basis. Now, what is this basis? Well, let's see. For example, the basis will be something that takes into account this. And you can see that here we have x2, x4, and x5. And here, well, we don't have in the second row x2 and x5, but we have x4. And here, we don't have any of them. So, basically, what you can rewrite here is something like this. Let me write this. Is 0, x2, minus 2x4 plus 0 x5. Okay, so we have now x1 and x3. There is something here that is x2. Well, x2 is obviously 1x2 plus 0x4, sorry, there is not much space, plus 0x5. Well, yeah, obviously x2 is equal to x2. And then you can write here x4. x4 will be 0x2 plus 1x4, of course, plus 0x5. Yeah, so you can see x2, x4, and just write by yourself x5 are the ones that are equal to themselves, are the ones that are independent, these ones, from the others. While x1, for example, is a combination of the other three. And x3 is a combination of the other three. Well, in reality, it just depends by x4. So now let me change one more time the color. What are these three vectors? Well, the three vectors are the ones that we can find in these columns. Now I can admit that it's not very well written. I would need more space, but just write this in a better way than me and look at the first one. Minus 3, 1, 0, 0, and if you go on 0 and 0. And the second one is minus 4, 0, minus 2, 1, and then 0, 0. We need 6 components as we are in a subspace of R6. So the result is, for the basis, is V1 equal to minus 3, 1, 0, 0, 0, 0. And V2 is equal to minus 4, 0, minus 2, 1, 0, 0. And finally, the last one, V3, is equal to minus 2, 0, 0, 0, 1, 0. And this is the result. This is a very important example. So if something is not clear, please ask me. It could be because I just had not enough space to do everything. So let me know if something needs further explanation. In the third paragraph of chapter 6, the Anton explains you how to derive and how to write, how to check for orthogonal sets and the orthonormal sets, the corresponding orthonormal sets. If you have a look at example 1 and 2, you can have a quite clear idea. Now, the orthogonal sets are very nice sets to choose a basis, especially if they are orthonormal. What's the difference between orthogonal and orthonormal? Well, the orthonormal is just the same as orthogonal, in which every vector has norm equal to 1. So if you have a set u1, u2, and u3 that is a non-orthonormal set, then you will have something like the norm of u1 equal to the norm of u2 equal to the norm of u3 equal to 1. Basically, working with orthonormal bases is absolutely the easier choice when you work in with vector spaces, and it's something that you have always done. When you create a set of bases, you always design something like this, that is an orthonormal space. If you have here this u1, x1 is fine, or x2 that are the bases. it is obvious that if the norm of x1 that is equal to the norm of x2 is equal to 1, is much more convenient if you want to express the coordinates of this point P. You can just write something like 1.2 and 2.3, and it is very easy to work with this because you know that the vector P will just be 1.2 times x1 plus 2.3 x2. You can see you are expressing a vector like a linear combination of the two vectors of the basis, and these two vectors are orthonormal because they are orthogonal, and that is the angle is a 90-degree angle, and their norms are just equal to 1. Now this is the usual way you work, and so after all the difficult things that we have done until now, it's you are now doing dealing with something that you already know basically. Now there are a few important theorems in this paragraph that tells you basically that if you have a set of orthogonal vectors, then these vectors are linearly independent. And this is okay because you know that every time you have a set of orthogonal vectors like this one in 3D, for example, or in R3, let's see better, you know that if they are orthogonal, like in this case, you can express one of these as a linear combination of the others, because if, for example, you look at this one and this one, you know that these two can span this plane, and I don't know exactly how to design that plane, well, that's not the way, but they can anyway span the plane that is orthogonal to this vector. So this vector can't be expressed as a linear combination of the other two vectors. Another theorem that is very important is number 6.3.5. It says to you that every non-zero finite dimensional inner product space, that means for you any vector space, has an orthonormal basis. So if you have a space that is not trivial, so if you have any space basically that you're going to work with, there is an orthonormal basis that can span that space. This is very important. It's something that you can expect. Now, if you look at the proof, it is quite interesting. It's not very difficult. It's quite interesting. And basically, it leads you to the Gram-Schmidt process. That is just a step-by-step set of rules that lets you to convert a basis of some space into an orthogonal basis. The final step to convert the orthogonal basis in orthonormal spaces is really very easy, and you can learn that in this paragraph, in some previous section of this paragraph. Paragraph number 4 is the paragraph you were waiting when you enrolled in MBB and maybe even in BCA. So in this paragraph there is finally the explanation of what least squares are, how to solve a system, that means how to solve real problems. So basically we have to deal now with something of this shape, a system of equations that is inconsistent. Why is this inconsistent? Well, till now we have worked with systems that were usually consistent, and that is just a case that in the real world you won't find very often. In fact, even if you are studying a problem, just think to your field of research or area of interest. If you are solving a problem, there is a very good chance that there are some errors involved in the measurements, for example. So even if you know all the variables of your problem, I don't know, you're studying lung cancer and you think you know all the important variables or even all the variables. I know this is impossible, but think to any problem, even if you know all the variables involved, and you have a cohort of people and you measure those variables and the outcome for each one of the subjects in your cohort, for each one of these measurements, there will be some error involved. Having some error involved means that your function, that is some outcome, like a linear combination, let's say that f is a linear combination of a set of variables or covariates, even just 4, if you have something like this, so these 4 covariates determine the value of y, that can be risk of lung cancer or anything you want to say, well, if there is an error involved, that means that this one and this one and each one of these will have some error, and then the system used to describe this relation in a set of equations, that is this one, every time you want to write your equations for your cohort, you will get an inconsistent result because it's not perfectly equal, because there is an error involved in each observation. So what can we do? Well, we want to find a reasonable solution, basically. And this is the least square problem that you can read in page 367. Basically, it tells you that this system is inconsistent, but it tells also you that you can minimize the error. That is, you can search for the difference between B and AX and minimize this. You want to find how to minimize this difference, this norm. Now, in all this, let's try to clearly define each of these quantities. This is the outcome in your study, and this, A, is the matrix that contains your data. It is also called the sign matrix. You want to find X. This is what you want to find. In X, there will be the parameters that gives you the linear combination here. So X, that is often expressed like beta, there are the parameters that gives you the cocktail of how to mix the different covariates to obtain y. That is, how to obtain the final vector Ax that is the closest possible to B. How can we do this? Well, let's see. It's quite interesting. In the first step, the Anton just tells you something that is a general result. And it tells you that if you have a subspace W, and in this subspace you have a vector W, And then you have another vector that we call b, that doesn't lie in this subspace. And if you want to minimize, and let me change color, the difference b minus w, this is what you want to minimize, well, it tells you basically two things. That this difference can be made equal to 0, because b is fixed and w can be changed, but in any case w is confined to be on this plane. So it can make the difference between b and w equal to 0. In fact, you can change w can just turn around. And what tells you is that if you take w, so the question is, how can I choose w to minimize this difference? Well, basically, let's reduce by one dimension. If you have something like this, and this is b, and here you have w that you can choose here, or here, or here, and you can see these are all differences, b minus w. Where is the w that minimize these differences? Well, you know, the shorter one is the one that goes perpendicular to this axis. This one is the difference that makes your w, this is the w that makes your difference shorter. So basically, going back in this case, to find the w that minimizes the difference between b and w, you just make the projection of b on the space, subspace, capital W. So let's say that this is something like this. Okay, so this W, the red one, is the one that minimizes the difference b minus w, the length of that vector, b minus w. Okay, how can we write this? Well, we can write that w as the projection of the vector b on the subspace w. Okay, so we are able to find the w that minimizes this distance. And this is basically what we wanted to do. Let's see. We wanted to compute the solution to this system, but this system is inconsistent. So we can't find a solution for this. Instead, we can find the best solution for something similar. Well, we can find the best solution for this one, that is the exact solution of something similar. That is this other system. That is the projection of b over w. And how can we solve this system? Okay, this is where all the nasty things and chapters that you study in the first 2 weeks of Module 3 comes in. To solve that, we can make some matrix operations. And let's see, this is a way. For example, we can take b minus both the terms. So we have b minus ax that is equal to b minus the projection of b on w. You can write this. And then you can multiply the transpose of a for both the terms. Don't worry, you're not required to be able to see how to find the solutions in this way. This is already quite advanced, but someone did for you. So you can write this. Now, when you arrive at this point, there is something that you are now able to see. It is very important. And is this term. What is this term? Well, B minus the projection of P on W. What's that? Well, that is that vector that is orthogonal to W. Now, if that vector is orthogonal, what is W? Basically, W can be the column space of A. And then we know that that vector lies in the null space of A, and then AT. So we know that these and these are in fact orthogonal, and then this product is equal to 0. So our solution simplifies to these equal to 0, and that means that we can write AT B equal to, taken from the other side, AT AX. So this is the best solution we can find. And look, now we have everything except x, of course, because we want to find x, and so we can find x from here. But before going on, this is a very important result. And this is called the normal equation or the normal system associated with AX equal to B. That was our starting point. These are the normal equations of that system. This result is incredibly important because, as you can see, this is general. You don't know what the shape of A is or B. It's just that given any problem that can be expressed with matrices, so basically any problem, you can write a general result. And when you have a general result, you know what happens is that you can program a calculator, a computer. You can write a statistical package. And this is what every software house made. R, S+, SAS, Stata, whatever. They all use something like this, general results in matrix formulation to compute the results that you want, in this case, X. Why is matrix formulation easier? Well, basically, it's because I'm writing whatever the size of your data and then of your problem. You just have this simple solution, this simple equation, very easy to remember, very easy to write, and very easy to compute from a software point of view, because the only thing you need to focus is how to efficiently compute operations between matrices. Which operation we are going to see. So the normal equations are AT AX equal to AT B. These are the normal equations. Very good. Now, if you want to find X, because this is what you want to find, basically you have to get rid of this part. And how can you do that? Well, just multiply for the inverse of that part. So you can write that X is equal to ATA minus 1 ATB. But when can you write this? Well, this is the subject of theorem 6.4.3, You can do this if you can invert ATA. Okay, there is a condition. There is a condition to do this. And if ATA can be inverted, then you know that you have a unique solution. And this is very important. So, to have a unique solution, you have to be able to invert this. And what does that mean in real world? Well, sort of real world. That means that A, the matrix A, must have linearly independent column vectors. So, if you have a dataset in which you have, for example, cigarette smoked per day, and this is one of your columns with all your, for example, or your data, and then you have a pack of cigarettes smoked per day, then these two variables are not linearly independent, because if you have 20 cigarettes per pack, then you know that this number will be just 20 times this number. So in case you have something like that, you basically can invert ATA. And this is the subject of theorem 6.4.3, as I was saying. Then, if ATA can be inverted, you can find the solution, X. Now what? Well, now you can, for example, try to find the projection on W of B. What's the projection of B on W? Well, this is basically the second step. The first one is this. This is the fit. And are your parameters. This one is the second step. These are the fitted value. Then what's the projection of B on W? Well, this is just AX. And then where X is this one. So in this case you just have to write A times all that formula. And let me make some space here, because this is very, very important. Okay, let's go back. So A, then ATA inverted, then AT, B. Okay, so the fitted values, I'm doing something more than what is written in the Anton in this chapter, in this particular paragraph. But the fitted value is basically given by all this that depends only on your data times B, that is your outcome. And this is interesting. It's very, very interesting. In fact, you can give a name to this, but this is probably not the right moment to do this. The only thing that you need to look here is that if you have a vector B like this, and you want to project that vector on the subspace W, that is a subspace created by the columns of A, then you can use this term, that is a matrix, this projection. This is the way to project in general any vector, let me change color, any vector B on a subspace W. At this point you should be very happy, because finally everything is going to clear up a little bit. Now, I know that has been very intensive and very difficult to do. The third module is difficult, I know. But at this point should be also fruitful. You should be happy to be here right now. In the next paragraph is we can finally apply all these to real numbers, to real problems. That is always the final goal. So I will leave the fifth paragraph to you to go through. It is really much easier than everything we did till now. And it should be almost a pleasure for you finally to do the fifth paragraph by yourself. As usual, if there are problems, any problems, just email me on the discussion forum and I will be more than happy to solve everything for you. Thank you.